Everybody, this is section 4.5, zeros of a polynomial. All right, so we're going to start off with a simple little example, and then we're slowly going to go into the actual portion of what this actual section is all about. Okay, so first off, when it comes to, we're just straight little example is we're just going to divide these out. Okay, so remember back in the day we talked about synthetic division. So that's what we actually want to do here to make it easier. So if you guys don't remember synthetic division, you may want to go back and review what we did way back into the day in A4 to deal with that kind of stuff. Okay, but or if you guys remember, synthetic division is we want to find the C value where this is going to be, in this case, 1, right? Because it's going to see x equals 1, so that's our C value. So if we do synthetic division, this is going to be 1, -1, and 1, corresponding to coefficients. So if we go down, always multiply, and always add straight down, that gives me 0, and then repeat, right? 0, add, and that is your remainder there. So essentially, if you guys remember synthetic division, when it comes to it, it's always 1 degree less, right? So in this case, instead of starting at x squared, this becomes now x. We have 1x plus 0 itself, right? Literally that. And now we have the remainder. Yeah. So the remainder is 1 over x minus 1. Remember, that's how we actually did it there. So that's one way of actually doing this. So how we actually want to write this is, well, we can write x squared minus x plus 1 in this format now itself. Okay. In other words, if I divide it, it gives me, if I add these two together, it gives me this back. Okay. However, there's another way we actually call it, so it's called the division algorithm. So the division algorithm says if I multiply basically the quotient times the divisor, and then if I add the remainder, that's the same thing as writing itself. So what that means is, without the fancy terms, is let's just do a quick little example. Let's suppose we want to divide 3 into 5, for instance. Okay, so 3 goes into 5 once with 2 remaining, right? So what this is saying is 5, the original function we had to deal with, is the multiplication of what we divided by, so 3, times the quotient, which is 1, plus the remainder, which is 2. And as we see, right, 3 times 1 is 3, plus 2 gives us the 5. So that's how we want to write this question out here. So I can rewrite as x squared minus x plus 1 as literally what we divided by. So it's just x minus 1. That's what we were divided by to begin with. Times what we found out to be, which is just x, plus the remainder, which is just 1. So if we literally multiply this, right, distribute this out and add the 1, we should get that back. And we actually do. So in other words, it's just another way to write complicated polynomials together. Okay. So why don't we try the example here out using this division algorithm. So again, we're just going to write the function now using the derivative algorithm way it's doing it. So again, right, when it comes to these cases, we're going to be doing synthetic division to make it far easier to, do long division itself. So in this case, we have x minus 3, so the c value is going to be 3 in this case. So it's going to be 3, and coefficients are 3, 4, and -1. And now always bring down the first one. So this is a 3. Multiply gives you 9. Always add straight down gives you 13. Multiplying, that gives you 3 times, what is it? 39. And that gives you 38 as your remainder. So therefore, to write this format, so f of x, or the function 3x squared plus 4x minus 1, now becomes, well, you first multiply what you were divided by to begin with, which is x minus 3. Okay. Now times what we actually got. So remember, this is always under now. So it's, instead of 3x squared, it's now 3x plus 13, and then plus a remainder of 28. Okay. So why don't you guys try b out for yourself? I'll give you guys a quick second to pause it, and then we'll do it together. So 3, 2, 1, pause. Okay. So let's try this together. So same thing, right? This concept is c is going to be now -2 because it's going to be x equals -2, right? If it's easier, you always think of the opposite sign to make it easier, things like that. So notice this was a +3, and the top one here was a +1 based off that. All right, so if we do that, now we do synthetic division. So this is going to be -2 plus 5 and then -8 as our coefficients. And always rinse and repeat, right? Bring the first one down no matter what. multiply gives you a positive 4. Always add down gives you 9. And then we rinse and repeat. So negative 18, which gives you negative, what, 26, I believe. So now finally, so we write it into the format we want. So therefore, it's going to be what we divided by, so x plus 2. So times what we got. So in this case, it's going to be negative 2x plus 9. Again, right, always 1 degree, so it's just be an x there. This is no x's. And again, plus the remainder, or in this case, minus the remainder because it was a negative 26. So that's the division algorithm itself. Okay. You do this more when it comes to linear algebra, and you go into actual programming is the most important thing you guys should actually do this about. But little fun stuff there when it comes to it. However, when it comes to our section in this case is going to be the next theorem down here. It's called the remainder theorem. All right. So the remainder theorem is very similar to what we talked about earlier. However, the remainder is very important when it comes to finding zeros of the polynomial. Okay. So the remainder theorem says that f be a polynomial. If f is divided by x minus c, the remainder is literally f of c. So in other words, we don't have to actually do this synthetic division finding what the remainder is. All we have to do is plug in the function, or plug in the c value into the function, and we will literally see the remainder itself. So in other words, no need to do this portion here. And that will come up a little later as why it's so important. Okay, actually in a couple minutes. So next one is called the factor theorem. Okay, so the factor theorem says let f be a polynomial, then x minus c is a factor if and only if the remainder is actually 0, which makes sense, right? If, for instance, this is not a factor of 5 because the remainder is not 0, right? So in other words, if I do 3 divided by 9, so 3 is a factor of 9 because it goes in evenly, right, with no remainder. That's what this is corresponding here as well. Okay? So let's try some out. So a little funky, kind of miswrote it here. It should look like this. Okay, so do a little funkiness when it came to the programming stuff, but it's okay. All right, so that's our function itself. Now what we want to do is what is the remainder when we divide by each individual case? So let's do A real quick. So in this case, right, we're dividing the same thing process we did here, right? We're essentially dividing. So we need to find the C value associated with it. Now notice the pattern, right? That's what I mean by it's going the opposite sign. So since it's x plus 2 and our general solution is x minus c, therefore our C value actually is going to be negative 2. All right, so since we want to find the remainder, you can use remainder theorem. In other words, we're going to plug in the C value into the function, and that guarantees us the remainder we actually will be having no matter what. So we just plug it in. So we got to figure out what f of negative 2 is in the function. All right, so this gives me what, negative 8. And this gives you positive 4 times a negative 4 gives you negative 16. And this is minus 5. All right, so the grand total would be negative 29. So that would be remainder. So again, right, if we literally did synthetic division, that would be our remainder no matter what. So again, I'll give you guys a quick seconds to pause it and try B and C yourself. So 3, 2, 1, pause. All right, so now let's try them together. So in this case, C would be positive 5, right? I'll put a sign. So therefore, if I plug in 5 into our function, and just simplify, right? So 5 cubed should be 125. This should be, I believe, 100. And this is minus 5. So total should be 20 as your remainder. Okay. And then finally C. C would be negative 1. So we plug in negative 1 into the function. So this is negative 1, negative 4, and negative 5, negative 10. Okay. Now, here's the thing. here we have A, B, and C. So the now question becomes, using the factor theorem, are any of these factors of that? And hopefully you say no, right? Because they're not zero. That's the main focus when it comes to it, right? So if these remainders were literally zero, therefore this one or one of these will be a factor of that, meaning it goes in evenly if we actually do synthetic division or long division itself. Okay? So that's called the factor theorem and the remainder theorem, respectively. Okay? All right. So now let's go on to the next page. Right? So this one is, well, so before we go any further, the main goal of this entire section, before we go any further, is to literally factor a polynomial down to its zero size. So last section we were able to graph polynomials broken down already. This time is, in this case, is, well, what if they're not broken down, right? So what if they're literally given to us like in this format here? Let's say there, and ask you graph this. Okay, well, we know rules when it comes to, you know, if it's curly or W's, depending on the rules, but what if, you know, they're not given to that format? And that's what the main goal is going to be about. So in other words, basically being able to graph any polynomial like this and break it down into its product of zeros, and therefore, again, using the rules we did in the section to simplify and then slowly sketch it out depending on the rules we have. Okay, all right. So before we go any further, let's just do this example. So the first thing is we want to find the sign changes of f of x and f of negative x. Okay. Now what this is saying is, well, if I just look at the signs, right, I just count. So this is f of x. I just want to count how many sign changes we actually have, starting from left to right. Now if I go from here to here, for instance, that counts as one sign change, right? I go from negative to positive, so that's one sign change. So here to here, well, that's positive, positive. That's not a sign change, right? So that doesn't work. Here, so you go from positive to negative. That's another sign change, a total of two sign changes. And then finally, negative to positive, that's a third sign change. So we have three total sign changes in f of x. Okay. Now we're going to do the same thing for f of negative x. So that means we're just going to plug in negative x everywhere and see what happens. Now, if you guys remember your rules when it comes to and odd powers and the negatives as well, is if you have an odd power, this negative will also become a negative. If you have an even power, this negative becomes a positive. So essentially, all you're looking for is what happens to the negative. So since it's odd, this becomes a negative times a negative gives you a positive 3x to the 7. And same thing applies here. So this is a negative odd power, so therefore this becomes a negative x on the outside, and times that positive 4 gives you negative 4x to the 5th. This is an even power, so this is going to be positive, so it's the same. And then the 5 doesn't change because it doesn't have an x. All right, now from here you can do the same thing, using a count how many sign changes we actually have. Again, starting from left to right. So none. So there's one here, right? Positive to negative. Another one over here, negative to positive. That's 2. And then positive, positive, so none there. So in the f of x function, we have 3 sign changes, and in the f of negative x, we had 2 sign changes. Okay, so in the next video, you're going to figure out why that's so important and how to break down a polynomial into its zeros itself.